Chapter 7 concerns itself with the properties of solutions, something that it calls colligative properties. So we'll start out first looking at what the difference is between pure liquids and then the behavior of those liquids once you turn them into solutions. I'm going to look at the difference between intensive properties for pure materials and colligative properties for mixtures and solutions. We'll look at the process of making a solution in the first place, and then we'll look at the types of intermolecular interaction that occurs inside a solution. There are 4 different types. And then that will lead us to the actual physical exhibition of physical behavior. And we'll look at the difference between cohesion and adhesion. And we'll look at colligative properties in boiling point, vapor pressure, and osmosis. And then at the end, we'll come back in and do a small number of math problems. Intensive properties are something that, if we thought about it really carefully, might actually be a surprise. But because we've grown up experiencing them the way that we have our entire lives, we just take them for granted. We know that pure water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. At least it does at sea level. And here's the thing. If I took a beaker of water and I put a thermometer in it and a Bunsen burner underneath, and I set to heating that liquid would get hot and then it would start to boil. And when it starts to boil, the temperature on the thermometer reads 100 degrees Celsius. And it stays at 100 degrees Celsius until all the water is done boiling. And if I repeat the experiment on a larger scale, I get the same answer. That water boils at 100 degrees Celsius no matter how much of it that you have. And in fact, if I took another heat source, another Bunsen burner, and put it under here, or maybe another 2, and I tried harder, it wouldn't matter. Water boils at its own boiling point, and it freezes at its own freezing point. And those numbers are independent of amounts and independent of how hard you try. That's called an intensive property, a property where the amount of sample does not change the answer. And we see that in pure materials. When we add an impurity to a pure liquid, we see something change in its physical behavior. So let's take something that we've experienced and that we understand. Let's take salt and water. If you add an impurity like salt to water, what we find out now is that salt water does not boil at 100 degrees Celsius, and it does not freeze at 0 degrees Celsius. In fact, it does something different. So this represents a beaker with pure liquid. Each of the dots is a pure liquid particle. What I'm going to do is add some impurities. I'm going to add some red dots. And what happens now is that those red dots just act like spacers. They're in the way, they're obstacles, and they prevent the liquid from interacting with each other the way that it was previously. We'll come back and look at that shortly. But the interactions between the liquids, not the same anymore. And what that does is it changes just how physically difficult it is to either freeze or melt. Now, in order to boil, you have to take a liquid and escape into the vapor phase. You have to get enough kinetic energy that you can escape and join the gas phase. Well, these impurities are stopping the liquids from escaping the vessel. They're just physically in the way. They're obstacles. And what that means is that it just became more difficult to boil. And we see that salt water has an elevated boiling point. Adding an impurity elevates boiling point. So the boiling point of salt water is over 100 degrees Celsius. This is something that we know because we add salt to the boiling pot when we're cooking something so that we can cook our food at a higher temperature. This is something that we've understood for a while. We just didn't know why it was happening. And the process of freezing involves these liquid particles sticking together and making a three-dimensional matrix of solid. And look what the red dots are doing. They're obstacles, again, stopping the liquids from getting together and freezing. So we see that salt water freezes at a temperature below 0 degrees Celsius. We have depressed its freezing point by adding an impurity, and we've elevated its boiling point by adding an impurity. And again, this is something that we know. When there is ice on our driveway, we throw some salt on it because the salt will make the ice melt. It makes the process of melting more difficult. So it happens at a temperature that is lower than 0 degrees Celsius. Now here's where the colligative part comes in. Because if I had a driveway completely full of ice and I went out and just sprinkled in a tiny amount of salt, I would expect nothing. I would expect very little to happen. But if I added more salt, I would expect my iced over driveway to unfreeze. So the effect that you get by adding an impurity depends only on the amount of impurity that you add. So if I add more salt to salt water, then I make its boiling point get higher and I make its freezing point get lower, and it depends only on how much I add. Colligative properties depend only on amount. So it's time to take a closer look at what those interactions between the liquid molecules were. We've seen them be disrupted, and we've seen it change a physical aspect of the bulk material. In order to take a closer look, we have to go back to the periodic table and mention something really important again. This side of the periodic table, the far right and towards the top, those atoms are electronegative. Electronegativity is the ability of an atom to pull electrons towards itself. Remember, the left-hand side of the periodic table gives its electrons away. The right-hand side of the periodic table pulls electrons towards itself. Those atoms, the nitrogens, oxygens, fluorines, and chlorines, these highly electronegative elements, going to pull electrons towards themselves in a covalent bond and change the way that that molecule behaves. Let's take a closer look. Here's the most important thing to know. Water, the molecule, is polar. The central oxygen is electronegative. It pulls electrons towards itself, giving that oxygen a small negative charge. We use the symbol delta, that's a lowercase Greek symbol d, delta, to mean a small change. The oxygen is a little bit negative, and these hydrogens are a little bit positive. This means that every molecule of water, because it is bent, has a negative end and two positive ends. And we know that positives are attracted to negatives. So these waters are going to stick to each other, and they will stick to other things that are in solution also. Let's look at those types of interactions. The first intermolecular attraction that we'll look at is called an ion-dipole interaction. We know that ionic materials, like sodium chloride, like salt, where we have a metal from the extreme left of the periodic table and a non-metal from the extreme right of the periodic table, when they dissolve in solution, they ionize and dissociate and become sodium cations and chloride anions. Now, because water is bent and polar and has a negative end and a positive end, what we'll see is that the water will put its negative oxygen end pointing towards the positive sodium. So the cations attract solution, attract these solvent molecules, but they're all oriented the same way, that the negative end of the water points towards the cation. And conversely, the chloride that goes into solution, well, it attracts attention from water through water's positive end, from where the hydrogens are. And it looks like we need about 11 water molecules to completely encapsulate an ion like this. This is called a solvation sphere, and part of the way that ionics dissolve in water is that the water helps, it facilitates the ions from being separated, because the water itself can put its positive or its negative end towards the ions. It helps them separate. The next attraction that we'll see is called dipole-dipole attraction, and it's going to occur between two polar covalent molecules. The molecule we're going to use is acetone, just as an example. Now, acetone has a polar bond. Carbon, group 4, oxygen, group 6. Oxygen is electronegative, which means electrons are being pulled towards this oxygen, making that oxygen be a little bit negative, leaving this carbon a little bit positive. When molecules of acetone meet each other, they stick together. That this oxygen, being a little bit negative, will be attracted to that carbon, and so the molecules will self-align and order themselves this way. This is a dipole-dipole interaction. Remember from an earlier chapter that the difference in electronegativity that generates a polar bond results in that bond having a dipole. And then depending on the three-dimensional shape of the molecule, if the overall molecule results with a net dipole, then these are polar molecules and they stick together. The next type of interaction is very important. It's called hydrogen bonding. And hydrogen bonding only occurs in very special cases. There's only a handful of molecules that can do this. It's going to happen in covalent molecules that are polar and are also this descriptive word, protic. Previously, we'd just seen acetone, and acetone is aprotic. It's incapable of doing hydrogen bonding because the electronegative atom in acetone did not have a hydrogen directly attached to it. But in water and also in alcohols, we see that the electronegative atom, that would be the oxygen, does have a hydrogen directly attached to it. That makes this bond very polar because hydrogen is in group 1 and oxygen is in group 6. So I have a big disparity in electronegativity. So not only are all of these oxygens negative a little bit, and all of the hydrogens positive, what I also have, I have lone pairs of electrons on the electronegative atoms. So we're going to start by pointing the negative oxygen of this molecule towards the positive hydrogen of another molecule. But also I'm going to point the hydrogen of this molecule to the oxygen of another one. And all of these interactions just consolidate. And it turns out that in a sample of water, all of the waters are holding on to each other, that each individual water is capable of making an attractive interaction, one of these hydrogen bonds, to 4 other molecules of water. And they happen between the lone pairs of electrons on the oxygen and the hydrogen on a neighboring molecule. Now that is supposed to be a straight line, and that the hydrogen bond is from the hydrogen of one molecule in a straight line to the lone pair of electrons in another. And remember, this is 3 dimensions. It's only 2 dimensions on the board, but it's happening in reality in 3 dimensions. Okay? This makes water very, very sticky. Water molecules love to attach to other water molecules, which when we think about what we see in nature is no surprise, because raindrops turn into puddles, which turn into rivers and ponds and lakes, and then ultimately turn into oceans. Water tends to find other areas of water and then stick together. The last intermolecular attraction that we'll look at is the weakest. It's called a London dispersion force. I think our textbook just calls them dispersion forces, and these are the result of induced dipoles. They're displayed by all molecules, not just polar molecules, so we don't have to have an already built-in dipole in the molecule. And what happens is that any 2 molecules, we have electrons in the bonds. So this is a non-polar molecule. It's called tetrachloromethane. It used to be called carbon tetrachloride. It's an industrial solvent. Well, there are electrons here, and there are electrons here. And electrons are negative. And negative charges, like charges, repel each other. So when these 2 molecules come close to each other, we get a repulsion between the molecules. Well, what if the electrons on this atom pushed the electrons in this molecule away so that they moved further to the other side of the molecule? Well, this would end up being a tiny bit negative, and this would end up being a tiny bit positive. I had electrons and I pushed them away to the other side of the molecule. Electrons are negative, so as the electrons go away, they leave a little bit more positive behind them, a little bit less negative, really. And so I get a very mild attraction between what is negative and what has just become a tiny bit positive. All molecules have this, so that all molecules can be cohesive. They can stick together to a certain extent. This is incredibly weak. This is the weakest of the four forces that we'll see. So the higher the level of these intermolecular attractions that we have inside a sample, then the more cohesion, sticking togetherness we have. And cohesion is going to exhibit itself a number of different ways. A couple of the ways that we recognize cohesive liquids when we see them is that we see surface tension. We see that the liquid surface seems to hold together and avoid being disrupted. And we can see, insects land on a liquid surface, and the insect doesn't sink because the mass is insufficient to break the attractiveness that the liquid molecules hold for each other. We also see this show up in a meniscus, which is a curve in the surface of a liquid's surface when it interacts with a boundary. You'll see a meniscus when a liquid and a glass wall combine together. They don't meet at 90-degree angles. There'll be a little bit of a curve. And here we've got adhesion. That's two different things sticking together. Adhesion is when two different things stick together. The water is sticking to the glass surface versus the water sticking to itself, which is cohesion. This is an example of surface tension. The metal paperclip, even though it's more dense than water, is refusing to sink because the water molecules are being highly cohesive. They're sticking together and preventing the metal from breaching the surface so that it can get down to the bottom of the container. A little poke should allow density to find its rightful place in the world. Let's have a look at some of the factors that affect the process or the rate of solvation. There are three big things that are going to affect the rate, and our book includes a fourth one. Particle size. Okay, so if I have to dissolve a rock of salt in a given amount of water, it makes complete sense to me that I should smash that rock into smaller pieces. The reason being that because the solid is a three-dimensional shape, if this is my rock, then the water can only dissolve the part that it touches. If I break it into smaller fragments, then the water gets more surface area for it to interact with. So decreasing the particle size increases the surface area of the solid that is available to dissolve. So that one's specific for solids dissolving in liquids. Agitation. Okay, so if I have a beaker of water with a lump of salt in it, again, the water can only dissolve where the liquid interacts with the solid. And what happens is that the liquid interacts with the solid. Let's pretend this is salt, and it dissolves the salt. And then over the course of a few minutes, I have an area of salt water that shrouds my particle of solid. Over here, elsewhere in the beaker, is still pure water, but I've got salt water close to the salt solid. If I give this thing a stir, then I disperse everything around it. Now pure water can get to the solid surface again. So shaking or stirring, any form of agitation, will allow fresh solvent to get to the solute. Remember, a solute dissolves in a solvent to make a solution. This is something that is a diffusion effect, that if I make the area of high concentration of salt water diffuse into the bulk liquid, then I allow fresh solvent in to do my solution. And then there's temperature. Temperature's effect is kind of obvious. If I want to dissolve salt in water, and it's a competition, and I have to do it faster than you, well, I'm going to smash my salt into small pieces, into a powder if I can, and I'm going to use hot water, because experience has told us that solids dissolve in hot liquids more than they dissolve in cold liquids, and they dissolve in hot liquids faster than they dissolved in cold liquids. But if I wanted to dissolve a gas in a liquid, I would completely turn that around, because experience also tells us that dissolved gases go into cold liquids better than they go into hot liquids. Remember, in a solid, the particles are very close together. In a liquid, they're further apart, and then in a gas, they're very, very far apart. And gases respond to kinetic energy, the energy associated with motion, heat energy, more than liquids and more than solids. So if I have a dissolved gas and I raise the temperature, it affects the gas more and before it affects the liquid. So the gases want to turn back into the gas phase and escape from being in solution, which is why when we want to keep the fizz in our carbonated beverages, in our Pepsi Colas and Coca-Colas, we put them in the fridge, because the bubbles stay in the solution better when the liquid is cold than when the liquid is hot. The other thing that the book mentions that I have not put on the board is how much is already in solution. So it is possible for a solution to just run out of the capacity to dissolve more solute. We've seen this in a lab previously. It's called the saturation point. I have not included it on this list because it's a specific thing, whereas these are all fundamental. So we know that solutions behave differently than pure liquids, and we've identified different types of attractions that are holding the molecules together. Let's see if we can make this work for us. Let's see if we can identify something useful that we can pull out of all of that information. The colligative properties, let's see what the solutions reveal about how much they're holding in solution. Okay, so we know that adding salt to water elevates its boiling point and depresses its freezing point. And if two of us did the experiment side by side, where we took the same volume of liquid, let's say we take 100 milliliters of water, and you add 1 gram of sodium chloride, and I add 8 grams of sodium chloride, and we put thermometers in there, and we see what temperature our solutions boil at, those solutions will boil at different numbers because I've got more impurity, I've got more solute in my solution, having a greater effect of disrupting the water's ability to boil. So, knowing that more solute changes the number, could we just reverse that? And if we look at the numbers, find a way to figure out how much solute there is? Well, yeah, you do that experiment a number of times and you write your the mass or the molarity of your solution versus its boiling point, and you plot a trend. And now when I say I've got a solution, a salt solution, and it boils at 102 degrees Celsius, you can look back on that graph and find out, I know what the concentration of salt in your solution is. This is useful. So now we can take just a physical observation, melting or boiling, and turn that into a concentration of solution. That's useful. There are two other things. One is vapor pressure. Now, we looked previously and we saw that if I have liquids in a container, then some of that liquid, we've all been around liquids that you can smell them. Yes, they're still liquids, but some of that liquid has managed to get into the vapor phase. Well, all liquids do this to a certain extent, some more than others. The ones that do this a lot, those are called volatile. A volatile liquid is one that turns into a vapor or into the gas phase very, very easily. These boil at low boiling points, and if they're flammable, then we have to worry about them. So all the liquids push a small amount of their molecules into the gas phase. And if we closed this up and sealed it, I would be able to measure the pressure that the liquid is exerting above its surface. That's called the vapor pressure. And every time I add an impurity, I make the process of vaporization a little bit more difficult. So again, what I would do is I would take the pressure, the vapor pressure of a pure liquid, add a little bit of impurity, record its vapor pressure, add a little bit more, record its vapor pressure, build up enough data to build a graph. And now if you present me with an impure sample, I can just find its vapor pressure and then reverse engineer what its concentration is. And we can do those problems in math. The fourth thing that we can measure is something called osmotic pressure. That's a little bit more difficult. It requires a little bit more of a description, and that's what we'll do now. Osmosis is a special kind of diffusion. So let's look at what diffusion is, because this is the more general approach. Diffusion is a spontaneous movement of solute from an area where it is high in concentration to an area where it is low in concentration. Now, when we see this from the outside, it looks like something mysterious is happening and that something is driving this and that there must be some kind of energy involved with this motion. And outside of just the kinetic energy of everything moving at room temperature, that's all there is. Because what we're seeing is just simple probability. That if we look at this is a container that contains water and a dissolved salt. So the red circles are solvents, in our case water, and the black is solute, in our case an ionic solid. If we start the day with a high concentration here, and all of these particles are allowed to move because there's enough kinetic energy in the solution, what we'll see is that those particles will drift. And as they drift away, and they even out, they're just going to find the place where it is most probable to happen. And it turns out that the most probable thing is for them to be dispersed randomly and evenly. And so you start the day with a concentration of solute, but over the course of time, it just evens out. That's just probability. Now, there is a chemistry concept allied to this. It's called entropy, and entropy is all about disorder. And this is more disordered than when we started and everything was all in one location. All in one location would be ordered. Spaced apart would be disordered. And there is a natural tendency of everything in the universe to become disordered, to increase in entropy. So this is what we call an entropic effect, and that's just how diffusion works. And you'll have seen this yourself, that if you put a colored flavoring in a glass of water, that flavoring might all settle at the bottom to start with, but then over a course of time, the entire glass is the same color, where the solute has evened itself out over time. Osmosis is a type of diffusion, but there are fundamental important differences. Osmosis is diffusion of the solvent, not the solute, the solvent. And instead of just being allowed to move, it's going to pass through a barrier. This is biologically important because the barrier in biology is the cell membrane. We're going to call this partition a semi-permeable membrane. Semi-permeable means it's going to allow some things to pass through, and it's going to block the movement of other things. One of the things that it's going to allow through is water. So if we find ourselves in this situation where I have a solution here, and this solution is higher in concentration than this one only has a small number of dissolved salts. Two things could possibly happen. One is we could just allow diffusion to happen and the solute would move and even each other out by diffusion. But there's this semi-permeable membrane here, and the membrane is not allowing the salt to travel, but it will allow the water to travel. And so in order to even the concentration in both sides out, the waters move from this side to that side until the balance of waters to solutes on both sides is even. This has dramatic biological importance. There are several medical conditions that are directly responsible to osmosis. Let's do some worked calculations. The equation that will find the new boiling point or freezing point of a solution is delta T equals Kmi. Delta, that's a capital delta in the Greek alphabet, Delta means change. Capital T means temperature. This is the change in temperature. K is a constant, and it's a unique number for each individual solvent. So if we're looking at an aqueous solution, we would look up the constants for water. And water has two constants, one for boiling and one for freezing. The constant for boiling for water is 0.512 degrees Celsius per molal. And for freezing point, K is negative 1.86 degrees Celsius per molal. We're going to make boiling point elevate, and we're going to make freezing point depress. So this is always going to be a negative number for us. M is molality. Now, molality is slightly different from the concentration that we've seen before. We've previously seen molarity with an R. This is molality. Molality is the concentration that we use when the temperature changes. And molality is moles of solute divided by kilograms of solvent. Remember, molarity was moles of solute divided by liters of solution. So this one's ever so slightly different. And then I is something called the Van 't Hoff factor, which basically just is the number of particles in solution. Covalent materials, when they go into solution, will remain intact. Ionic material, when it goes into solution, will split apart into ions. So if our material splits apart into two things, it has a greater effect. So we're going to count the number of particles that are in solution. Okay, let's put some numbers to this. Let's use this equation. At what temperature will a solution of 4.50 grams of potassium chloride, when dissolved in 100 grams of water, what temperature will that freeze at? We're going to use this equation. Delta T equals Kmi. The K that we're going to use is the value for water when it freezes, which is a negative 1.86 degrees Celsius per molal. I is the number of particles in solution. And we're using potassium chloride. Potassium chloride is a strong electrolyte. So when it goes into solution, it splits apart completely into two particles. So my answer for I is 2. When the chemistry majors do this question themselves, we actually use an ever so slightly different number. It's a tiny bit more complicated than just counting the number of particles, but this will do. It will do. And then M, lowercase m, is molality. Not molarity, molality, which is the moles of solute per kilogram of solvent. And we know that there are 100 grams of solvent and that there are 1,000 grams in a kilogram. So the kilograms of water is the 100 grams that we have times 1 kilogram divided by 1,000 grams, which gives me 0.1 kilograms going into the bottom line of my calculation. The moles of potassium chloride, well, moles is equal to mass divided by formula mass. So I had to go look on the periodic table and find the atomic masses of chlorine and potassium. And when I add them together, I got 74.5 grams per mole. So my 4.5 grams in the question, my mass, is divided by the formula mass, 74.5, and then that number is divided by 0.1 kilograms. And I put the numbers into my equation. Negative 0.186 times 0.60 times 2 equals a freezing point depression of 2.2 degrees Celsius. So if I had two beakers, and one contained pure water, 100 grams, and one contained 100 grams of water with 4.5 grams of potassium chloride in it, then the pure water would freeze when the temperature hits 0 degrees Celsius. But the solution would not freeze until the temperature outside is minus 2.2 degrees Celsius. That's a depression in freezing point for a solution versus a pure solvent. Let's look at the other calculation that's in this chapter, osmotic pressure. So we said earlier that osmosis is the flow of solvent, probably water, into a solution that is separated with a boundary. It's called a semi-permeable membrane, and the water flows across that barrier and into the solution. Well, as the water is flowing in, if we wanted to stop that flow, we would have to apply an external pressure to the solution. So the osmotic pressure is the minimum pressure that must be applied to the solution to stop that inward flow of water across the semi-permeable membrane. Osmotic pressure, pi, is equal to I, that's the Van 't Hoff factor, that's just the number of particles that's in solution, times m, which is molarity. This is our moles per litre concentration, times R, which is something called the ideal gas constant. Now, if you look that up, it comes in many different forms, but the one that we're going to use is 0.0821 litre atmospheres per mole per Kelvin. Litres are a volume, atmospheres is a pressure for gases, moles is a concentration for solutions, and Kelvin is a temperature. And the T here is temperature. Now, when we use temperature in a calculation, we typically don't use Celsius, because Celsius can be a positive number or a negative number. That can throw the meaning of the numerical answers completely off. So when we use temperature in a calculation, we convert our Celsius numbers into Kelvin. Kelvin is an absolute temperature, and 0 degrees Celsius on the Kelvin scale is equal to 273 Kelvin. Kelvins never go negative. That's what absolute zero means. You can't get any colder than absolute zero. Okay? So we'll write up a question and we'll put some numbers in there and we'll make these numbers make sense. So let's calculate an osmotic pressure. If I have a 100 milliliter solution that contains 1 gram of sodium chloride salt, what is the solution's osmotic pressure at 25 degrees Celsius? 25 degrees Celsius is room temperature. My equation is pi equals IMRT. I is the number of particles, and sodium chloride, when you dissolve it in water, splits apart into 2 particles. So I becomes 2. M is moles per litre. So I need 2 things to figure this number out. I need, on the bottom line right here, that I have 100 milliliters in the question, while there are 1,000 milliliters in a litre. So my 100 milliliters is 1/10 of a litre. And molarity is moles per litre. So I've got my number of litres calculated. Now moles is mass divided by formula mass. So this is the mass of sodium chloride divided by the formula mass of sodium chloride. And there is 1 gram of sodium chloride in the question. And if I look on the periodic table and I find the mass of sodium, 23, and the mass of chlorine, 35.5, and I combine them together, that tells me that the formula mass for sodium chloride is 58.5. So 1 divided by 58.5 divided by 0.1 gives me a molarity of 0.171 moles per litre. R is a constant, it's the universal gas constant, and in litres atmospheres per mole per Kelvin, that value is 0.0821. And then that just leaves me temperature, but temperature needs to be expressed in Kelvin in absolute terms. Room temperature is 25 degrees Celsius. Add to that the 273 degrees conversion factor, that 0 degrees Celsius is 273 Kelvin, and that number becomes 298. 2 times 0.171 times 0.0821 times 298 gives me an osmotic pressure of 8.36 atmospheres. An atmosphere is exactly what it says it is. It is the pressure of the atmosphere. So what you experience right now at sea level is 1 atmosphere's worth of pressure. To stop pure solvent water pushing through a membrane into this solution with this concentration of salt, you would need to push 8 times atmospheric pressure onto that solution to prevent that transfer of water from happening. That's what our osmotic pressure means.